The topic of today's demonstration is Otoacoustic emission, automated ABR, and acoustic immittance hands-on with AudioSmart and aScreen. Today, Maya Petrova, our clinical assistant, will assist me during the live demonstration. So we will start with Otoacoustic emissions, theory, applications, and then proceed with live demonstration. Then we will cover acoustic immittance tests, tympanometry, and acoustic reflexes. Then we will proceed with automated ABR, and we'll show again the live demonstration. Today, I'm going to be the patient for all tests. Then I will show briefly how to work with software, Neuro Screen Manager, PC database software for our handheld devices. And in the end, I will cover some sales aspects of AudioSmart and aScreen devices. Specifically, I will describe our solutions for these tests in more detail. And we will end this talk with questions and answers session. Okay, so this is our audiological product line. And as I mentioned, today we will cover the second half of this product line, specifically AudioSmart devices in different combinations, and aScreen device. But first, I would like to briefly cover the topic of newborn hearing screening, because since we want to describe otoacoustic emission tests today, it is very tightly coupled with this topic, with the screening. So today, in many countries of the world, there are universal newborn hearing screening programs. So every baby who is born undergoes this newborn hearing screening. And after this, there are two possible outcomes, pass or refer. And there is a group of children who got the refer result. They should undergo at a later stage the hearing diagnostics. And then intervention, being hearing aids or cochlear implants, probably. And after that, a lengthy period of rehabilitation. So otoacoustic emission is mostly used for screening. Let's now discuss how this test is recorded and the principles of the response. Let's start with ear anatomy. So as we reviewed yesterday, our ear consists of three main parts: outer, middle, and inner ear. And today we will cover second middle ear part and inner ear part as well. Now let's look closer at the cochlea. This is the ancient drawing. And let's look closer to the outer hair cells. These are tiny hair cells within the cochlea, which actually generate the otoacoustic emission. So the principle of transient evoked otoacoustic emission generation is the following. The outer hair cells within the cochlea, they react to the upcoming sound waves, and specifically these sound waves get transformed to the basilar membrane movements in the cochlea. And these outer hair cells react to these movements. They shrink or change in size. And these movements then generate the electrical response by the inner hair cells, which is transferred further along the pathway by the auditory nerve. So the principle of transient evoked otoacoustic emission acquisition is the following. The stimulus is provided through the probe, which is inserted in the ear canal. The stimulus is usually the broadband click, which is also called a non-linear click, which is most often used for this test, because non-linear, it means that it is actually a sequence of 4 stimulus, which is repeated constantly. One stimulus is large with a positive polarity, and then there are 3 smaller stimulus with negative polarity. This is done to compensate for the non-linearities inside the cochlea and hair cell mechanism. So we produce this stimulus through the telephone or speaker inside the probe. And then the outer hair cells generate very soft sounds in response, like an echo sound. These sounds get captured by the very sensitive microphone inside the probe. And you can see the resulting recording as a waveform on the screen, and also its spectrum. And as you can see, this waveform typically mimics the structure of the cochlea. So as was in the previous slide, the receptors inside the cochlea, or the hair cells, they are located on the whole length of the cochlea, from base to apex. And each group of receptors or hair cells is tuned to the specific resonance frequency. And so at the base, there are highest frequency receptors, and at the apex, there are lowest frequency receptors. And so the response mimics this structure. It starts with higher frequencies and ends with low frequencies, because lower frequencies are at the apex. There is some time needed for the sound wave to travel to the apex. Another type of otoacoustic emission test is distortion product otoacoustic emission. This test uses different type of stimulus, which is two pure tone stimulus, like they're called usually F1 and F2. And the cochlea generates distortion product emission on the third frequency, which is calculated by 2F1 minus F2. So it's important that two independent speakers produce these two pure tones, which enter the ear canals and middle ear to the cochlear's outer hair cells. And we get this response also by the microphone. We record it by the microphone in the probe. So the clinical applications of otoacoustic emissions, aside from screening, are the following. We can also use, for example, TE-OAE to detect hearing loss. It is present at hearing loss up to 30 dB. The response is present. So if there is no response, the hearing loss is of higher intensity level. And distortion product otoacoustic emission is also present at hearing loss, but at higher intensity, up to 50 dB. And also another important application for DPOAE is when we test up to 12 kilohertz, higher frequencies. It can be used for two purposes: monitoring of drug ototoxicity and noise-induced hearing loss, which is especially important for occupational hearing preservation programs, for example, in some noisy industries and so on. And another possible application is as part of test battery, including also ABR, probably other evoked potentials and so on, to distinguish between types of hearing loss, sensory or neural, or maybe auditory neuropathy and so on, as part of test battery. OAE on the screening device looks like this. So TOA on the left, DPOA on the right. And in the end, this is the screenshot from our devices, but during the recording, but in the end, there will be response pass or refer. And also it's important during the test to select the ear tip of proper size to seal the ear canal completely. And also it's important to fix it on the OAE probe properly, so there is no gap. Maya will show it soon. And also it's important, especially when testing babies and premature babies, to place the probe correctly in the ear. Suggested by us, the probe position is shown on the photo on the left. And so the baby should be sleeping with the head on the side. Now, before we continue with tympanometry, I invite Maya to show otoacoustic emission live demo.
Okay, Hello, I'm glad to see everyone today. And now we go on and start our practice. Before I need to say a few words about this procedure. As Michael said, it helps us to evaluate the state of the cochlea. And actually, we can use both of our portable device for this aim, aScreen and AudioSmart, but today I will show you how to perform transient evoked otoacoustic emission and distortion otoacoustic emission test using aScreen device. Before we start, we need to look to the patient outer ear canal and to fix if there are any contraindications to put the probe in the outer ear canal. After that, they need to choose the proper size of the probe tip. You know that we have a lot of different sizes and shapes of probe tips. For example, if you test the baby, you need to choose something like that, cone shape with small diameter of the hole. And if you test an adult, you will choose, for example, this size, mushroom shape probe tip. After you look in the outer ear canal, you will make a decision. Now we can go to other patient. We use the aScreen connecting to the smartphone. Yes, okay. I run the program. And now we are ready to fix the probe. Okay, thank you. To fix the probe into the ear canal, if you test an adult patient, you need to pull up and backward. And after that, we can choose the side and press. Let's start from the transient evoke. And we see that it occupies only a few seconds and we get the result pass. It means that we have a reliable response in different frequency bands. In this particular patient, we have a result in 200 and a half, 300, 3000 and 3000 and a half kilohertz. And from all of 6 frequency bands, it is 50%, and for the screening protocol, it's enough. So we can save, we can select or create a new patient. And insert all the necessary data. For example, something like this. And press here. Now we have the patient cut and we can go further. Let's try to make the distortion product or the otoacoustic emission. On the right side, we see the calibration process of the telephones, and now we see the gray line is the noise level, and the red line is the level of response. And we see the big difference between them. It means that our response are more in amplitude than the noise, and it's a reliable response in every frequency band. We have 4 frequency bands now. We can set the result pass. And let's go to the template setup. I will show you what can we do there. So we go to the test settings. Let's look to transient evolved Otoacoustic emission template. We see that we have some default templates for different types of environment, depending on the noise environment we can choose. And we also can make our own templates. We need to name it. And after that, we can change all the parameters in this template as we want. For example, we can make, for example, more signal to noise ratio pass criteria if we testing our patient in the clinical condition, not in screening, for example, but in more clinical center. And also we can make the pass count more, for example, in such conditions, not 3, but for example 4. And in such a way we can change our templates for different conditions. The current template will be the last template which you edited. So let's look for distortion product template. We see that we have 3 default templates, and we can make the new template. We see that the mode here as in default is 4 by default, but we can change it. Michael has said before that it's very useful to use high frequency distortion product Otoacoustic emission test when with suspicious ototoxicity or maybe noisy condition, hearing loss in some patients. So let's try, for example, to make 12 frequencies next time. And we see all other we can change as well. So let's try to repeat with our new template. You see that the calibration is occupy all the 12 frequency bands. You see the noise here is great in the low frequency band. It's more than a response, but it's in our condition here, not in the clinics. And after that, all the responses are reliable. So we also get the result pass because we have reliable answers more than in 50 frequency bands. So this manner we perform such tests. Save, and we can print the result if we have the Bluetooth printer, or you can export it to the near audio screen manager. Michael will show you later how can you do it.
So I am back to my presentation, and we will continue with tympanometry topic. So actually, there is a group of tests for middle ear analyzer device like AudioSmart, and they're called acoustic immittance, and we will start with tympanometry and then proceed with the other ones. So what is tympanometry? Tympanometry is a test where also the probe is used inside the ear canal, but in this case the probe, in addition to delivering the sound, for this test it is called a probe tone. It is a low frequency tone. Also, the pressure is changed inside the sealed ear canal. And during this change of pressure, relative to the atmospheric pressure, ambient pressure. The plot, which is called tympanogram, is drawn on the screen. Tympanogram is a plot of ear admittance versus the relative to the pressure. And what are main device components of the tympanometer device? It consists of probe tone speaker, of the monitor microphone, also very sensitive microphone, pressure pump, which is a new compared to the Otoacoustic emission probe. This is a new one here, since we need to change the pressure, and manometer, because we need to measure this pressure as well, and also ipsilateral reflex loudspeaker. So again, two speakers are used in this case for these tests. One is for probe tone, which is used to measure the admittance, or the admittance is the inverse of the resistance. So it's the measure of how well the middle ear transforms or transduces the sound. So briefly, I will also describe the principle of tympanometry test. So you can see the sealed ear canal on the left picture. When we apply the air pressure plus 200 dpa, then in the middle there is ear canal at 0 dpa at ambient pressure. In this case, the eardrum is relaxed. In the case of additional air pressure, it is tense, and also in the case of reduced pressure, it also becomes tense, but in another direction. And so if we look at the compliance or admittance a bit to the right from this picture, the best compliance or the best ear transduction is at ambient pressure. Normally, it is at ambient pressure. So at ambient pressure, the tympanic membrane and middle ear structures, they offer the best sound transduction to the other parts of the hearing analyzer. And when we look at the right hand side picture on the slide, this describes the principle of how exactly do we measure the admittance of middle ear. Because actually we measure the total admittance, which consists of admittance of outer ear, so the part of the ear canal before the tympanic membrane, and the second half, which is actually the middle ear structures. And the way we measure this is the following. We first apply some pressure, like plus 200 decapascal. And with this pressurized condition, the eardrum is acoustically opaque. It does not transduce the sound to the middle ear. And so in this condition, we measure the outer ear admittance. And then when the air pressure changes in the ear canal, the tympanic membrane or eardrum becomes acoustically transparent. And so we measure the total admittance. And since for this test we need to measure the middle ear admittance, we just subtract the total from total admittance the outer ear admittance, and we get the middle ear admittance. This is shown also on the tympanogram here. So this graph shows total admittance. So outer ear admittance at plus 200 dpa plus middle ear admittance part, which is called compliance. So the analysis in this test mainly consists of classification of the tympanogram waveform. So there is a classification system developed by Dr. Jerger at 1970. So it is a classic system used still today for classic tympanogram types. So they range from type A, which is a normal tympanogram, to different other types like AD and AS, B, which is almost completely flat, and C, which has a misplaced peak. And the main values which we analyze in addition to the tympanogram in this test are the following. Tympanogram peak pressure, which is also shown on the picture on the left. So it is pressure at the peak of the graph of the chart. Then the equivalent ear canal volume, which is basically the admittance of the outer ear I was talking about before, which is measured at 200 dpa usually. Compliance, which is a peak compensated admittance at the tympanic membrane. So it is actually the part of admittance which is comes from the middle ear. And tympanometric width, which is also called gradient, which is shown on the picture. It is also called tympanometric width. So it is a width of tympanogram in the pressure units dapa between the points of 50% of compliance on the tympanogram. Now, before this, I was talking of the classic tympanometry, which uses low frequency 226 Hertz probe tone. This value was chosen out of for historic reasons, and this is widely used still today, to this day. But there is a reason to use another frequency, which is 1 kilohertz. And it is important to use when testing infants before 6 months of age. Now, this is a case study, an example of why it is important to use another probe tone frequency for children, small children. Because let's have a look. When we measure classic tympanometry using low frequency probe tone, on the left-hand side, we measured the right and left ear tympanograms, and they both look normal. The tympanogram peak is within the normative rectangle, normative region. But when you look at another tympanometry results on the right-hand side, using the 1 kilohertz probe tone, you see that for the left ear, we have no peak. We have flat line, flat response. And in this case, it was confirmed that the child, the infant, had otitis media with a fusion in left ear. So it's important to use this frequency in order to not miss the middle ear pathology in infants. Now, another type of test in the acoustic immittance test group is a Eustachian or acoustic tube function test, ETF. This test is similar to tympanometry, but it involves recording 3 tympanograms in different conditions, patient conditions. So first we record normal tympanometry as usual, and then we ask the patient to perform a Valsalva maneuver to exhale against the closed nose, and then the tympanogram peak should move to the right to show the increased middle ear pressure. And after this, we ask the patient to do a Toynbee maneuver, swallow also with the nose pinched closed. And after this, the tympanogram peak should be moved to the left, shifted to the left. We will show it during the live demo today. What else I would like to comment about is that there are several ETF tests, actually. So the classic one, which I have described, is ETF1, or it's called also ETF-I, which means it is the test to be performed with intact eardrum. But there is also a test called ETF2 or ETF-P for perforated eardrum. It is also called inflation-deflation test. This test we will not show today because it is not available in the Audio Smart device. So, and the third type of test is ETF3 or ESRT, which is used for admittance recording, long-term recording. It is used usually for electrical stapedius reflex or ESRT test. I will also show it later today. Now, acoustic reflex tests. This is another type of test for acoustic immittance. In this test, the end result, as you can see on the right, is a chart displaying changes in acoustic admittance over time. And this is recorded when the loud stimulus is applied to the eardrum to the probe. And in this case, usually the frequency-specific stimuli, short frequency-specific stimulus is used of different frequencies, for example, 500 Hertz as shown on the example here, and other frequencies, for example, 4 kilohertz and so on. And usually this test is done in sequence, so the stimulus gets gradually louder and louder in order to find the acoustic reflex threshold, because this reflex occurs only with quite loud stimulation, about higher than 70 dB stimulation above hearing threshold. And this loud stimulus causes bilateral contraction of stapedius muscles, which are smallest muscles in the human body. And this change is reflected in the change of admittance. So we see it on the acoustic reflex chart. So the clinical value of acoustic reflex is that, first of all, there are no other hearing diagnostic techniques that can give you so much information in such a short amount of time. This is a quote from the James Hall, one of the experts for this test and for audiology in general. And so, as you can see on the left in the picture, there are typical patterns which can be found during the reflex recordings, especially when you record in addition to the ipsilateral reflex, which is recorded with the probe in the ear canal. We can also record contralateral reflex, where the probe tone is still applied by the probe, but the contralateral, the opposite ear, is stimulated with tone bursts by the headphone, which is called contralateral headphone. And so, recording left and right side ipsi and contra reflexes, we get a lot of information and we can find out different patterns of pathologies, where the response is absent or where it is present, depending on this. And the final test in this group of tests is reflex decay, which is similar to acoustic reflex in the recording principle, but as opposed to the short stimulus used for reflex threshold test, in this test, decay test, we use a long stimulus, 10-second long, continuous stimulus, also tone burst, usually 500 or 1000 Hertz. And during this stimulus, it also produces the reflex, because this test is done at the intensity typically 10 dB higher than the threshold of the reflex to evoke the reflex for sure. And in this case, in normal patient, there will be almost no reflex decay, so it will maintain almost the same the same strength. The reflex will be present for the whole duration of the stimulus. But for some pathologies, the reflex may decay very quickly. So the normal value is that decay should be no more than 50% over the whole 10-second time. Now I will also briefly cover the automated AABR screening test, and then we will proceed with the live demonstration. So AABR screening is used recommended to use for especially prematurely born infants and other risk group children. Because these babies have high risk of auditory neuropathy spectrum disorder. And this type of hearing loss can be detected reliably only by using the AABR. It will not be detected by OAE test alone. So this is how this test will look like on the Audio Smart device. First, there is a demonstration of how to place the electrodes. And then the test is very quick. We will show to you that it takes just several seconds, usually, and up to 3 minutes, but it's only takes that long when usually there is some kind of pathology. So it takes long. It usually means that there will be a refer result. And the algorithm for the detection of the response uses a multiple component analysis. So there is chirp stimulus also used to increase specificity of screening for higher than 90%, which is important for screening. But also our audio smart device has ability to do diagnostic ABR as well. So if, for example, we got a refer result from AABR, we can confirm this result with diagnostic ABR, at least to get a preliminary result, because it is still recommended to follow up with full diagnostic ABR device examination, but still you can get approximation of the response of the diagnostic result with audio smart device. And it can show you also the ABR waveform. You can put the wave markers, wave 5 and other markers. And stimulation can go up to 60 dB with probe. And if you need higher intensity, it is possible with headphones. And the main limitation of this ABR performed with handheld device like AudioSmart is that it is only one channel device. So you will get only one waveform for each recording. And also, since it is a handheld device, of course, there are compromises in the amplifier quality. So it is a bit more sensitive to the noise level in the test room in general. And the result will be probably not as smooth and clear as with our Nero audio device, for example. But usually it is enough to get an idea, at least if there is a wave 5 or no. So the Nero Audio Screen Manager is a PC database software which can be used to store the results done with AudioSmart and aScreen devices. The results can be transferred to the PC completely wirelessly by Bluetooth technology. We will show it also briefly today. And you can view also the examination results, test results in the software, and also print the test report, and, for example, export the data to some other hospital information systems. For example, this software supports GDT protocol used in Germany and some other countries. And this software is also cross-platform, so it works also on macOS. This is the diagram of how this software is the key to integration of AudioSmart and test results to the specific clinical information systems, clinical hospital information systems. So this is the example, for example, how to use GDT requests to integrate, or the integration can be used by the raw data, for example, JSON format files. And JSON is an open plain text format widely used in the web today for web services, for data exchange. So it should be no problem to use it if required. Now we will proceed to the live demonstration, and I again invite Maya to perform the test on me.
Okay, let's go for our practice now. You see different things and accessories that help us to perform the procedure. We start with the acoustic immittance test, and the critically important in this test is to choose the proper size of probe tip, because the probe must be put tightly to the ear canal. It is a critically important now. So I pay your attention to this. We need to make a calibration process before we perform tympanometry. I will show you now with the help of such test cavity alone, or the test cavity which is integrated in our holder to AudioSmart device. Also, what do we need to the acoustic immittance test? Then we will perform acoustic reflex tests. We will use this contralateral headphone to perform the contralateral acoustic reflex. And also, we need this holder to put the plus TIMP device on our patient to the he's comfortable. So let's come to Michael. We see the audio smart in the holder, and let's okay. Okay, the new patient now. Let's perform calibration process. We go to a TIMP daily calibration, and the device asks us to place a probe in the test cavity. In our case, it is integrated in the holder. Please put the probe tightly, and after that, press start. So the device measures volume and check calibration. No, we want to do the calibration of coefficients of acoustic reflex now, because you need to do it only one time at the start of the working or after your audio smart will remove with a new plus TIMP device. So no, in this case. So this TIMP daily calibration is for daily using, and the calibration of acoustic reflex coefficient is only one time you will calibrate, and it occupies 5-6 minutes for it. Now we are ready to perform tympanometry. We go to the main menu. Now I will position plus TIMP pump in the holder. So I will put it tightly enough without any gap. So I use the mushroom shape for Michael, the big size. And if you test an adult, you will choose other type, for example, cone with a small hole. And now I put the probe. I move the pin up and backward tightly enough. I don't, oh, okay. So the left ear. Okay, some artifacts here because of the Michael movement. So I repeat, please. No, let's try to.
I think the fitting is not very good.
No, let's try to put. Okay. Okay, more smooth form now, and see that the compliance peak and the pressure peak is in the normal values. It can get different values individually, but if it is on this square, it's good. And the shape is a form, so we see the peak. In this case, if we want to look to the particular numbers of the pressure peak, or for example of the compliance, we look down here. They see the compliance is on the low border of the normal values, 0.4, and the pressure peak also in the normal values, nearly to the ambient pressure here. The volume of ear canal is 1.1. In adult patient, it can be, for example, from 0.6 to 1.5 milliliters, so it's in the normal values. And this is the gradient. Michael has said before that it's the width of the tympanogram on the 50% of the amplitude of the tympanogram. So if the tympanogram become more wider, it's become closer to the B type, especially if we don't see any peak in it. So we can also look to the numbers and make some conclusions. If we want, for example, to make one more tympanogram in this patient, we put here to the plus button, and we can choose the necessary frequency or the probe tone. Now we have 4 different probe frequencies. So let's try to make on the 678. They see that we can also make standard or extended pressure range. In some cases, it can be useful. Then we have the peak in the non-typical place, for example. So we go. We have also a peak here, but you see that in this frequency of probe tone, we don't have any norms window. It is because in the scientific literature, the main norms are for collecting for 226 Hertz only. And here they see only on the orienting of the curve, it must be upward, and they look on the peak. Is it here or no? And so you can plus other types of tympanogram here. After you finished, you save the results and can print via Bluetooth printer if you have. After that, yes, we save. Then you patient, we did, so we can select, for example, to the last one. After that, we can make an acoustic reflex. I need to put the probe. It is put before, and I will put the contralateral headphone on our patient, and I will connect it to the plus timp block, and I can start the acquisition. So we see my template occupy all the necessary frequencies of the stimulation tone. We see the IPSI reflex on 500 Hertz, and now contra reflex on this frequency too. So one by one in my template, I will show you how you can set up the template after the finished. So after that, we go to the 1000 Hertz, and you see the threshold for detecting the reflex. Now the curve will move against it, and the reflex will be detected. And the last one is for it's for additional information that it's a reflex too on the intensity above the threshold of the reflex. So they see the reflex is here, and the last one additionally, according to my template. And they see the 4000 Hertz, the first via probe and the second contra via contralateral headphone. And we can see in more details our curves of the reflex. They see that the device collected some curves before reflex, which is on the 85 dB in this case, and one after the reflex, additional. If we want, for example, we have some artifacts or so on, we can restart the particular acoustic reflex searching on particular frequency one more time pushing here, but now we have the good quality of curve, so we won't do it. We can save, print. Now let's look for acoustic reflex decay. I ask Michael that he must be still during the detection and not swallow very frequently and not breathe very deeply. So 10 seconds will be pretty high tone in the probe. I should note this information to my patient. I see the pressure peak which came from the tympanometry of Michael, and the stimulus will be 90 dBs. It's higher than the acoustic reflex threshold on this frequency. I can change it before testing will start, and the duration by default is 10 seconds. I also can change the frequency if I need, but mostly in routine practice, 1000 Hertz is used. So let's see, the sound is going and the acoustic reflex is come. The muscle is constructed and the sound switch off, the muscle relaxed, and the decay is only 7%. It's in normal values. Michael have said before that normal values is up to 50%. If it is more than 50%, it is about some inflammatory processes, retrocochlear, in retrocochlear area, or if it is more than 90%, is a vestibular schwannoma. For example, cancer in this area, retrocochlear, it's a very important site. Then you have more than 90% of decay. It's a normal picture. Now, before we go, okay, let's go and do ETF function test, and after that I will show you the setup of templates. Now we will go ETF on the intact tympanum, as Michael said before, ETF1, and it requires our the instructions of the patient, what to do during the test. And the device will help us with the helping windows. So let's start. The first step is the registration of tympanometry. Okay, the probe is go out, I think. Let's Okay. In some cases, it is useful to put the probe one more time. Maybe the patient is moving or something, and the probe go out, and you will see it because there is no peak. Let's see that the peak is on the -7 dpa, and after that, the device ask the patient to pitch the noise, close the mouth, and breathe through the nose and ears to make the Valsalva maneuver. Okay, let's try. And we see that the peak actually go out of our window, I think. So in these cases, so the peak goes to the positive values which are not in our screen. In such cases, what can we do? We can ask the patient to swallow a little bit to make the pressure more negative, or we can make the template setup and make an extended window for the our pressure values. Now let's try to rewrite. Now maybe the pressure, no, let's go to the setup now and test settings, team settings. And now let's create a new template and make the start pressure 400. So we will use the template for tympanometry, and for ETF too, we then extended values for pressure in decapascal. Now let's try. Because of Valsalva maneuvers, put it out. Okay, let's try one more time. Okay, the pressure came to the ambient value, and they ask Michael to make the Valsalva maneuver one more time to breathe out to the ears with a pinched nose, but not so not so strong. Okay. Okay. One more time, our peak is go of the values. So let's go to the Toynbee maneuvers, and the peak will came to our values again. Now Toynbee, pitch the noise and swallow. So we decrease the value in our middle ear. Then the Eustachian tube works normally. Yes, so the peak on the Valsalva maneuvers will be out of our value graph. And on the Toynbee, you see that the peaks came on the almost on this place there it was before. So the Michael's tube works good. He can make the pressure in the middle ear growing and reduce using these maneuvers. So actually we see the difference between between second and first peaks, and between third and second peak. And in normally, it must be more than 10 decapascal, they see that the Michael's tube working good enough, and he is the patient which didn't need to be instructed because he know everything very good. But in some cases, some patients don't understand how to perform these maneuvers, and if you see that the PICS is standing on one place, it doesn't certainly means that it has some problems with his tube. Maybe you need to repeat the testing after more deeply instruction. In some cases, it's useful. Then you make Toynbee maneuvers to give the patient the glass of water and to make some swallow with the water. So it can be useful in such cases. Then your patient doesn't understand your instruction. Okay, we can save. Then the tympanic membrane is not intact. For example, have some perforation. This test you can't use. You should use ETF2 or ETF perforated, which will be available in our future device. I hope soon enough. We finished all the tests of acoustic immittance, and I will show you the templates setup. So we go to the test settings and choose the necessary procedure, for example, tympanometry. And also, as you have seen, this template is for ETF function 2 template. So I create the new one, but they see that we have two default templates for tympanometry by itself and for tympanometry according acoustic reflex. It means that then you finished the tympanometry, you will have an opportunity go to the acoustic reflex in this test window, and you don't need to go to the main menu. In these cases, you choose this template. And also you can create your own template, name it, as I have done. And after that, you can change some parameters, the start and the stop pressure, the pressure change speed. In such cases, maybe you need the lower speed of changing. You can make it lower. By default, it's the faster one, fastest. Also, you can switch off an after stop, for example. And this bar is for acoustic reflex. For template, there is tympanometry with acoustic reflex. You can manage the process of going to the acoustic reflex after the tympanometry here. Now let's look to the settings of acoustic reflex. Default settings. Here you can change anything, as in also all other default templates. You see that the sensitivity is 0.05 milliliters, and the step of growing the intensity in searching of acoustic reflexes, you can change it in the default templates. But in your own template, you can change it. You can change the acoustic reflex mode for picture that you will get during the acquisition. We use auto mode previously in Michael, and we see all the curves in searching process. Then you will put here in screening, you will see only the one curves, the actual one curve. And also An external stimulator is a mode. Then you use audio smart with a system of cochlear implant, and the stimulus will go through the system of cochlear implant. And our device will detect is there any reflex in this moment of time. So in this particular way, you should use such type. You can also change the sensitivity, the step before reflex. You see that in some cases it can be 2 or 1, but the device will show also 3 steps if they were 3, and 1 step after reflex additionally. And also you can edit the sequences. You see here a lot of frequency of stimulation tone, also noises. And you see that you can manage the intensity of starting. You can make it some more, for example, if you want. And you can switch off some frequencies if you don't need them, for example. So you can make your own sequences in this template. It's very useful in some cases. For example, you don't need, if you don't want to perform contra reflexes by to all of your patient, you can switch off the contra side and make only IPSI reflexes, for example, and so on. So it's the template setup for acoustic reflex. And I think we can perform automatically ABR tests. You see that the Audio Smart has such electrode adapter. Using this, we connect electrodes located on the patient to Audio Smart device. And now let's prepare the Michael. Let's put the electrodes and connect it to the Audio Smart. We have put before 2 electrodes on the mastoids, on the left and on the right side. And now we should put 1 electrode more on the forehead. I will prepare the skin as we done yesterday. Firstly, I will degrease the skin with a spiritus. If you make AABR in babies, you don't need to use spiritus. You can use only abrasive paste. And in the adult patient, you should use alcohol previously. And after that, gently rubbing the skin. We will use hydrogel electrodes today, but also you can use other types of electrodes, for example, cups electrode if you want, because they also have the touch proofs which can be connected to the adapter. I shaped them twisted again to reduce the electromagnetic noise, and there are a lot of cameras and I don't know where to go. Thank you, Alexei. So we see, yes, we see that this adapter has a color coding to connection. So I connect the cables according to their colors. Yes, blue and green. We need only 3 cables. Instead of Neuro Audio yesterday, we use 4 because Audio Smart device register evoked potential using 1 channel, only IPSI channel. That's why only 3 cables. And after that, the probe is put. I will run an AABR left, and we'll see how good quality of impedance I have. So forehead is green. I connect. The right mastoid is right. And we can see the impedance is good. And I will connect the last one, and the test will start automatically if the impedance is good. So the left one and the C, the calibration, and the C, the grid, the probability percentage. The C, the line is the graphic of probability, almost the same as the C yesterday in the multi-ISSR tests. The same mechanism is here. So they see the probability is high enough, and it occupies only a few seconds, and then it go up for some time. We get the result pass. If the probability is low, long enough, or all the time is low, don't reach the threshold values, we get the result RFA. This test helps us to evaluate the state of retrocochlear part of auditory system. That's why it's very important to perform to the children. Then you have a suspicious on the lesion behind the cochlea. So the state of the cochlea you will evaluate with the help of otoacoustic emission tests. And if you have suspicious, then the lesion is back from the cochlea, you should perform an automatically ABR test to detect the state of the retrocochlear part, especially the auditory nerve and the brainstem. So this test is screening one, so it can be performed with the nurse or with the help of technician, and it doesn't require the visual inspection of the curves, which we made yesterday in the ABR. So we put some peaks and so on. So this test doesn't require such attention because it's totally automatical, and you get the result pass or refer. And after that, you will know what this patient should you do this. So you can say that this patient must go to the more deeply diagnostic with the ABR, for example, using the diagnostic device like Neuro Audio we have yesterday. So I think I can release the Michael.
So thank you, Maya. And now I will finish my presentation showing the Neuro Audio Screen Manager software. So I will share my screen again to show you the software. Sorry, I will switch to English. So I will again share my screen. Here it is. So as you can see in the top toolbar, it shows the device connection status. It's now connecting to Audio Smart device, and we will try to download some examinations. So let's try again. We will check on the device. Yes, the Bluetooth is enabled. Yes, okay, so it shows it's ready. And we see on the left-hand side one patient record in device and 9 examinations in device. And on the right, we see that they are all counted as new because we have not imported them before from this device to this database. So I just click download. And you see a progress bar showing the download process. This is done wirelessly by Bluetooth. Now the process is finished, and we see the test results here in the database. For example, here, yes, here you can see the test results which we have recorded today during the webinar. So for example, this is my transient Otoacoustic emission test. This is my automated ABR test. This is my reflex decay, and so on. So this is how you download and view the test results on the PC. Also, you can, for example, write to the device memory new patient record, new patient cards. So we click the button upload the device to device. And here we can select some patient records. By default, it shows untested patients. We click the arrow button to add them to the list to be uploaded to device, and then click upload, and it will appear on the device. And also, for example, if you remove some test result or patient, you can click delete. It is removed from this list, but it is actually going to the trash bin, and so you can go to the trash bin if you want to undo this operation. And you can click the button to restore from trash bin. And the test result was restored. Okay, and also from this software, you can click on the printer icon to create the report. The report can be, let me show you, for example, but the emission tests. You can actually click on the patient to get the report for all of the examinations of this patient. Or you can select specific exams or test results which you want to add to report. For example, I will select only TUA and DPUA results and click the printer button. And here you can see that software tries to optimize paper usage. It shows you right and left ear results. Oh, sorry. And so from this screen, you can also create a PDF file if you want just the PDF to store it somewhere. Or you can click the printer button to print it in the selected printer here. So what else to say? I would say that you can also export the data to JSON format I was talking about before in my presentation. And for example, you can import this JSON file on another computer. So that's how you can transfer test results between PCs if you want. And also the data, statistical information about patients' screening results, pass or refer, and which test is this result for, can be stored in the plain text format, another plain text format, CSV, comma separated values. This could be used also, for example, to open this file in Microsoft Excel or other spreadsheet software to analyze the statistical results of how many patients, for example, got the pass result and how many got refer result, and so on. All of this operation of screen manager software you can see in detail in our YouTube channel. We have a detailed video about this software where I show all the details. But here I will also mention that there is a settings button with a gear sign, and you can customize or set up the software how you like inside this window. Okay, so now I will finish the showing this software and continue with my slides presentation. So our audio smart device offers a very flexible choice of tests. You can initially buy only the tests that you need, and then you can add the modules that your growing clinic starts to require, for example. So thank you for your attention. Now we are finishing our webinar for today.